Hello, Calculus BC, and we are working on 9.1 parametric equations. So I know it's another 9 unit, and I really need to get the other ones reorganized. But this truly is Unit 9 for the AP classroom idea. Follows their guidelines. So another Chapter 9, and this first one we're going to talk about parametric equations, which I know you have very little um, experience with. So let's just talk briefly about what a parametric equation is. Parametric equations have a third variable involved. So our typical rectangular has x and y. Now we're going to move into three variables. Typically, we'll use the variable t. So it's going to relate an x equation and a y equation with a common variable t for time. So it's going to be really convenient. It'll help us when we move into vectors as well. We can talk about movement at a certain time and which direction it was moving horizontally versus vertically. So we can separate out a vertical and a horizontal movement. We can separate out horizontal velocity versus vertical velocity by using parametric equations. So I think you're going to like them. Parametric equations in the box says is if f and g are continuous functions on t, or functions of t on the interval I, then the equations x equals f of t and y equals g of t are parametric equations, and t is the parameter. So we can see how x is going to be written in terms of a t value, and y is going to be written in terms of a t. And both x and y each have their own separate functions to define them. You can sketch a curve of a parametric equation simply by substituting the value of t into them, the common variable between them. So the set, let me just see if I can narrow this point up. There we go. The set of points x, y also could be thought of as f of t, g of t, or at least what I'm trying to do is identify that there's two different functions, one pertaining to x and one function devoted to y, creating this parametric curve. Parametric curves have an initial point. That's different. And a terminal point. So there's a beginning and an ending to parametric equations, which sort of implies direction. Yeah, there is a direction to these curves as well. So if it starts here and travels this way, we can, towards the terminal point, uh, this was the initial point, we can pick up the direction of the particle movement. All right, so example one, sketch the curve with the following parameterization. X of t equals 2t. So there's it. It's kind of like f of x, f of t function. And then y of t is defined as t squared minus 1. So that's kind of like that g of t function, f of t function. So different equations. Now this is pretty common too, with t being defined as a minimal value of -1 up to a t value of 2. So we can run into our equation, into each of the equations and find out what x and y would be. That'll give us an ordered pair of x, y, which we can come to our normal coordinate plane here and graph out x, y. So common variable, -1 going in. So I would have 2 times -1 looks like x will be -2 when t is -1. And y would be what? -1 squared minus 1. So 1 minus 1 brings us to 0. So what I would go plot is the ordered pair -2, 0. So this is its initial point when time was -1. The next value, looks like that fraction bar got relocated when it went into a PDF form. This is -1/2. So 2 times -1/2 would give us -1. -1/2, -1/2 squared would be a positive fourth minus 1. So it sounds like that's going to be a -3/4. So -1, -3/4. This is -1, 1, 1, -1 over here. 2, 3, 4, 2, 3, 4. All right. When we put in 0, this will be nice. We get out 0 for x. When I put in y of 0, looks like I get out -1. So 0, -1. When we put in a half, we get out 1. When we put in a half, we're going to have a half squared, getting a quarter. Quarter minus 1 will give us -3/4 once again. So +1, -3/4. Putting in 1, we get in 2. Putting in 1, we get out 0. 2, 0. A little bit of symmetry to this. And then putting in 3 halves, looks like we'll come out with 3 for x. 3 halves here would be 9/4 minus 4/4, coming out with 5/4. So 3 and then 1 1/4. And put in 2, I'd come out with 4 for x. Put in 2, 4 minus 1 would give me 3. So I have the spot 4, 3. And then go ahead and connect them. There is a direction being plotted out, isn't there? And you can show the direction along that curve if you wish. Now, one thing I'm going to do is switch over to your graphing calculator and let's operate in parametric mode. So grab your graphing calculator, go to mode, and bop down. And normally we are running in function mode. So you're going to just move to the right and select parametric. You can hit enter to make sure it holds. Go to your y equals and you'll notice an update to the y equals. It now has two equations, x sub 1 t, y sub 1 t, showing us that x is dependent of t and y is dependent on t. So I put in my two equations. Where did I get my t value? Well, I just did 2 and then the x, t, theta, n button. So t is appropriate because we're in parametric mode. And then I put in my y, t squared minus 1. Before we graph, I want you to hit window and let's modify this window. So we know we were on a restricted domain for t, and that went from -1 to 2, so I put that in. I let the t step go by 1/12, I think is what I keyed in, just so I would get a fair amount of dots plotted, rather than just counting t by ones, which would only plot a few spots, like, it would have been those dots that we've plotted on our paper. And then for x min, just looking over, our x values, I just said, well, hey, we never went lower really than -1, but I put in -3 to 6 for my x values. I counted my x's by 1. So when I see my graph on my calculator, my tick marks are going to represent 1 unit. And then y min, I did -3 to a y max of 4 and a y scaling of 1. So my tick marks will be every 1 unit. Now you should be able to hit graph and notice that there's going to be a beginning and an ending. Mine did it so fast because I already had graphed it once. Yours maybe with yours you got to see that direction as it plotted out, that it went up like that. And then it definitely stopped once we hit that x value of 4, didn't it? That would have been when t was 2. So that's how you can plot out parametric equations. All right, on to number 2. Well, if we can work in parametrics, it might be a good idea that we can switch between parametric and rectangular equations. What are rectangular equations? The ones that you're normally used to. So normally we have like y equals 3x plus 7. That's a rectangular. It graphs out on the rectangular coordinate plane, doesn't it? Where we have x, y coordinate values. So those are known as the rectangular equations and a rectangular coordinate plane. Looking for an erase key, which I don't have here. Okay, bear with me. It won't give me, okay, I'll just try to erase. I'm at home and it does not hold our settings for smart. All right, here we go. Now, This first one says, to find the rectangular equation when you're given a parametric, eliminate the parameter t. We'll do that through substitution. So we have two equations, and I'm just going to bring them down into my workspace. So x of t equals 2t, y of t equals t squared minus 1. Now you can choose whichever one you want to solve it for t, but I think I'm going to use that first one. I'm going to use the x one. It just seems like it's pretty simple. So what I'm going to do here is solve for t. I want to express this now as a t equals value. And to do that, I would have x equals 2t, or 1/2 x equals t. Now what I can do is sub that into my y equation. Substitute into our y of t equation. And so what I'm trying to do is take it into the other form of the equation that I did not solve for. So it's kind of like solving a system of equations. The one you didn't use before, you will use now. And we know that t is 1/2, so I'll get y. This is now going to switch into a y of x equation. Watch this. Because t gets replaced with 1/2 x, which will get squared minus 1. Now we are in rectangular form. I have y of x equals x squared over 4 minus 1. And definitely the shape on this is parabola, isn't it? Yeah. And if it graphs out, we would get that parabola shape. Very cool. All right, equation or problem number 3. Given the parametric equations, eliminate the parameter. Well, we get to work with cosine and sine. So if you want, you have a little bit of space over on the left side. You may, I'll just give myself a little bit of space over on the left side. It's not as easy using the laptop. Just keep in mind, you're going to solve one equation for t, and then you'll sub into the other equation. That's essentially the steps we need to do. And okay, I'm going to bring my workspace here, update it with the two equations, and then just kind of consider which ones I may want to solve. I still think I'll solve for x because it's not that hard. Okay, so first thing I'm going to do is solve for t. And that would be x divided by 2 as step 1 equals cosine of t. Now, how do I get rid of cosine? I would have to cosine inverse both sides, right? So this will be a cosine inverse of x over 2, and cosine inverse of cosine would leave me just t. Now, I can take t and sub t into the y of t equation. So this is going to give me y of t equals sine. Replace t with cosine inverse of x over 2. I can squeeze it in there. And you know what I need to do? Because I'm no longer a t, this automatically just flipped to an x equation. So it's saying y of x is now sine of cosine inverse of x over 2. Kind of complicated, but hey, it's in y's and x's. So now it is rectangular. This is rectangular form. All right, on to finding derivatives. So we can do derivatives of parametric equations just like we did derivatives of rectangular. So the starting point for this, I've already got it started on my workspace. dy dx, which is our normal derivative work, can be thought of as dy dt over dx dt. And that is how we are going to find our first derivative when we're working with parametric equations. Why does this work? Well, maybe just give yourself a little explanation here. Notice that if I take dy dt divided by dx dt, that would be like taking dy dt and multiplying it by the reciprocal of dx dt, which becomes dt dx. Look at this multiplication. We could take dt over dt and call it 1, and that leaves me dy dx. Yeah, that is how we're going to take our derivatives, and that is why it works. So I have my two parametric equations, and I don't want to swing them back into rectangular, although I suppose I could. I'm going to work with it this way. So noticing that t is greater than or equal to 0, find dy dx. dy dx is going to be, I'm going to take the derivative of dy dt first. So what I'm just going to write out what I'm going to do here. I'm going to take its derivative and divide it by t to the 1/2's derivative, right? We have a dy dt on top, a dx dt on bottom. To do the derivative on top, the 1/4 out front's not going to bother anything. We'll just take the derivative of the inside. So I'm going to have 1/4 times 2t minus 0. So I'm not even going to put the minus 0. And the derivative of t to the 1/2, that'll become a 1/2 t to the negative 1/2. Okay, simplifying, I have t over 2, 1 over 2 square root t, and that's a t over 2 times a 2 root t over 1, multiplying by reciprocal, right? And looks like we get a final answer of t root t, or if we pulled our exponents together, we'd be adding a 1 and a 1/2 exponent, so we'd end up with a 3/2. Now, what did you observe here? Well, we do have dy dx, and it is in terms of t. That's interesting, huh? And most of the time, that's the way it's going to work out. Number 5, given x of t and y of t for t greater than or equal to -1, find the equation of the tangent line. Okay, you should know how to do equations of tangent lines, but it is an awesome refresher right here. So I'm going to give you a little left-hand space over on the right here, or actually over on the left. I needed to move to the right to get this ink. All right, so for a tangent line, just remind yourself, you need two things. One, we need a point, so like x, y. Second, we need a slope, a dy dx. Can we get those two things? If we can, we should be able to write it in y minus y1 equals the slope, dy dx, times x minus x sub 1. And there's that equation of a tangent line. All right, so let's get our dy. Yeah, let's get our point first. Let's go after the point. That might be easiest. We know the point is when t equals pi over 2. So I'm going to make a value of x of pi over 2. That's going to be at e raised to the 2, put in pi over 2. 2's are going to cancel. Looks like we end up with e to the pi. Now let's go after finding y. The y value at pi over 2 is going to be cosine of pi over 2. Knowing your unit circle, you definitely know that this is equal to 0. Okay, and now that gives me a value of, or an ordered pair of e pi comma 0. I'm just going to make a squiggle. Now let's go after our slope. And we want the slope when t equals pi over 2. To do that, we need dy dx, but that's going to be found by going dy dt over dx dt. dy dt is what? Well, it's the derivative of cosine. That's going to be a negative sine value. And the other one, derivative of e to the 2t, will be chain rule 2 e to the 2t. Now let's evaluate our derivative dy dx, evaluated when t equals pi over 2, gets us negative sine pi over 2, and then 2e 2 times pi over 2. Looks like on top, knowing our unit circle, sine of pi over 2 is a 1, so we'll have a negative 1 on top. On bottom, we'll have a 2e to the pi. Now, third thing, sounds like green, is write the equation, or our tangent line. So, y minus the y value of 0, you don't have to put it down if you don't want, negative 1 over 2e to the pi times x minus our x1. Our x1, remember, was e to the pi. All we had to do was go look at our pieces of information, and it was very easy. Suppose we could simplify this as negative 1 over e, 2e to the pi, x minus e to the pi. Very nice. All right, I think that's all. That brings us into your homework page. There are 16 problems to work on. Definitely do the ones at the end where you get into this AP practice. I have to say, I think these problems are really good for mimicking AP problems. If you do get stuck, because some of them are a little bit challenging and you haven't worked in parametrics before, unfortunately, use the answer key, in Schoology to help you out. Have a good day.